When we think of gases, we think of particles that are very far apart. And their size is negligible compared to their container. So you have a large volume, but very small particles. So gases are mostly empty space. It's that empty space that gives gas its properties. The ability to be compressed is because gases are mostly empty space. The idea that the particles are moving fast enough that you have these high pressures, that's because there's a lot of empty space. If there wasn't room for them to move around, they wouldn't, but they can, so they do. If we look at gas particles, they're moving quickly in all directions and randomly. You can't predict where a gas particle will go next. So when they're in this container and they're moving randomly, they collide with each other, and they also collide with the walls of the container. They hit the wall of the container, they bounce off. When that happens, it creates pressure. And when we talk about gases, we frequently talk about pressure. And pressure is the force that the particles exert on the container walls. So they hit the wall of the container and they push it out. It's a force. It happens over and over and over again. The same thing happens with the gases in our atmosphere. So the gases around us, nitrogen, oxygen, carbon dioxide, they collide with us and they create pressure. It's called atmospheric pressure. If you're at sea level, which we're really close to sea level, you have the whole atmosphere on top of you. And we call that 1 atmosphere pressure, or 1 ATM. And because of that, atmospheres are the most common unit of pressure that we use in chemistry. In physics, you use pascals, and here we use atmospheres. That's it. So in Indiana, we're at sea level or close to it. We have the whole atmosphere pushing on us. If you move to the top of a mountain, do you think the pressure up there is 1 atmosphere? No, it's less than 1 atmosphere because you don't have the whole atmosphere pushing on you. You've gone above the atmosphere at that point. Because of that, it takes less time to bake stuff up there because there's less pressure pushing down on it. If you ever look at the back of a box of brownies, they always have high altitude baking instructions. That's because at higher altitudes, the pressure isn't 1 atmosphere and it takes less time or a lower temperature. Inversely, if you lived in the bottom of the Grand Canyon, which most people don't, the pressure down there is higher. There's more atmosphere pushing on you because you're below sea level. And technically, it would take longer to bake brownies at the bottom of the Grand Canyon because there'd be more pressure pushing down on it. But that's the idea of 1 atmosphere pressure, atmospheric pressure. This is why when you go up in an airplane or you drive up a mountain, your ears pop. Your ears, your eardrums have become used to the pressure here. And as you go up, the pressure goes down your ears push out too much and they pop. On the way back down, your ears are not pushing out enough and they get pushed back in from the pressure. That's why your ears pop. It's all about pressure. We also use something called millimeters of mercury. It's another unit of pressure. There are 760 millimeters of mercury in 1 atmosphere. This came from old barometers that measure pressure. It would be a tube with mercury in it, open to the atmosphere. The atmosphere would push down on the mercury. It would rise in the tube, and they would literally measure it in millimeters. In Indiana, it would be about 760 millimeters of mercury tall. And then another unit that we use sometimes is torr. Same number as millimeters of mercury, just a different unit. They're equivalent. But these are your conversion factors. Questions? Okay, let me erase, and then we're going to talk about kinetic molecular theory. In the same way that Dalton's atomic theory described atoms, kinetic molecular theory describes gases and the way their particles behave. So the first part of kinetic molecular theory, gases are composed of tiny particles that are negligible in size compared to their container. AKA, gases are mostly empty space. Lots of empty space in gases because there's so much room, so much distance from particle to particle. And then on top of that, the particles are so small that there's just lots of empty space. Number 2, gas particles move randomly in straight lines and at varying speeds. We know this, we talked about this already, but gas particles, you can't predict where they're going to go next. They're moving in all directions. They collide with each other, they collide with the walls of the container. They're just random. Number 3, the forces of attraction or repulsion between gas particles are negligible except in collisions. The only time we talk about forces between gas particles is when they collide. Otherwise, they don't attract each other, they don't repel each other, they just move around each other like the other ones don't exist. It's completely random motion. There is no attraction between gas particles. Number 4. When gas particles collide, the collision is elastic, which means kinetic energy is conserved. So, for those of you who have not had physics yet, there are 2 types of collisions. There are elastic collisions and inelastic collisions. In inelastic collisions, the 2 things collide, and at the end of the collision, when the collision is over, they are not moving with the same average speed as they were before. They have lost kinetic energy. That doesn't mean they've lost energy. Energy is always conserved, but they've lost kinetic energy. One of them has, probably both of them have slowed down. Think of a car crash when you think of an inelastic collision. 2 cars are coming through an intersection and they collide. At the end of that collision, the average speed of the 2 vehicles is 0 or much lower, right? They've lost kinetic energy. Now, they haven't lost energy. That energy has turned into lots of things, like heat from the collision and sound and other things. But kinetic energy is not conserved here. Gas particles, when they collide, it is not like a car crash. They collide, they bounce off, and the average speed is the same as it was before. Just like the pool balls on a pool table. They don't necessarily keep moving as fast as they were before. One might speed up and one might slow down. But overall, the average speed is the same. Kinetic energy has been conserved. Same thing with these gas particles. They collide, they bounce off, and afterwards, one of them is moving maybe faster, one of them is moving slower, but overall, they're the same. The speed is the same. Elise?
So would them like hitting the edge of the container be elastic?
That's also an elastic collision. So if that gas particle is moving, say, 50 miles per hour, when it hits the wall of the container, it bounces off at 50 miles per hour. That is an elastic collision. In an inelastic collision, like a car crash, if you hit a wall at 50 miles per hour, you do not bounce off the wall at 50 miles per hour. That's a strange world to live in. You see the difference? These are completely elastic. All right, the last one, number 5. The average kinetic energy and kinetic energy is equal to 1/2 mv squared is of the particles is proportional to the Kelvin temperature. So kinetic energy is 1/2 mv squared. M is mass, v is velocity, speed, meters per second. How fast the particles are going, on average, they're not all going the same speed, but some are faster, some are slower, they have an average. On average, how fast they're going is directly related to the Kelvin temperature. And remember, the temperature in Kelvin is Celsius plus 273. 0 Kelvin. How fast are the particles going? 0. They're not going. They have 0 kinetic energy. As the particles go faster, the kinetic energy is higher, and the Kelvin temperature is higher. They're not equal, they're proportional. So the temperature in Kelvin is proportional to the average kinetic energy. Faster particles, higher temperature. And for gases, we only use Kelvin because we're talking about kinetic energy. Having a negative temperature implies negative kinetic energy, and that's not something we can have. So Kelvin only. Jonathan?
Do we need to know the proportion, like the actual number?
Nope, you just need to know that as temperature goes up, kinetic energy goes up, or kinetic energy goes up, temperature goes up.
It's for SRT tomorrow, I'm guessing.
Okay, thank you. Questions? All right, gas laws 1 is your worksheet for today. Do as much as you can.